Okay, so good morning, everyone. I'm going to give a little bit of a more in-detailed introduction to X-ray analysis. So Andrea showed the lovely things that eROSITA can do. And obviously with this collaboration, we want to encourage more people to work with us and also to make use of the nice radio and optical data that you also offer to us. And so this is a bit of an introduction to the tutorials that are going to come later by David and Pietro, sorry, in the opposite order. So Pietro first and then David, which will give a more detailed method of how to work with eROSITA data and how to do spectral modeling with BXA. And if you're interested in more details, you can also have a look at this link of a talk from Sophia Waddell from the 2023 workshop. She goes into also more detail about the X-ray astronomy parts, the introduction to it. But okay, I can't start this presentation without again showing this lovely image of the eROSITA first all-sky scan of the whole sky. So this is what the sky looks like in the X-rays. And so as Andrea was showing, eROSITA can scan the entire sky in 6 months. And this is the deepest X-ray map that we have gained of the X-ray sky ever. So you can see really the wide range of objects that it can detect, for example, supernova remnants, clusters of galaxies, X-ray binaries, and all these point sources in the background. Most of them are actively accreting supermassive black holes, so AGN. So really a wide variety of data. If I go to another telescope with this Chandra, I like to show this image because Chandra has a higher spatial resolution, so it can really go into the details of how these objects really look like. And here you see really the diversity of the X-ray sky with all these supernova remnants, and Centaurus A, for example, is radio galaxy, even Jupiter, which is emitting an X-rays. So really with X-rays, you can get a lot of intuition about how the physical parameters of the high energy phenomenon that are going on in these objects. So this is why you should maybe consider looking at your source in the X-rays, because you can maybe find out some interesting things about it. So we've had some lovely talks about radio astronomy and optical astronomy in the past 2 days. I wanted to use these two images to kind of show the differences between X-ray astronomy and those two regimes before. First of all, on the left, what I want to show is that with X-ray detectors, we're actually, we're individually looking at our X-ray photons. So they're very special to us. We come give them a little kiss every time we find them in our detectors. Whereas in optical astronomy, we have, a whole mass of these optical photons. We don't see, how tall these minions are or how energetic they are, how much they're jumping up, because we see them as like a mass altogether. And similar in radio astronomy. In radio astronomy, we work in more waves, the combination, the interference of these waves. Whereas in X-ray astronomy, we have really like the droplets of water that we know exactly when they arrive on our detectors, what energies they have, and what size they are. Of course, we can also, combine these droplets in these sort of stacking experiments, as Andrea was mentioning, to make deeper X-ray images. But as we know very precise information of our few photons that we get. But of course, yeah, we're all here in this workshop to kind of work together and form collaborations. So this is why I like to show this image, because together we are much stronger to combine all these wavelengths to get much more interesting information about our sources, to get a really holistic view of our sources. Okay, so how do X-ray telescopes actually work? Well, X-rays have a very high energy. So actually to focus them, you need to use these nested mirrors and using a small grazing incidence. So actually having a very small angle of incidence to these mirrors, otherwise they would get absorbed before they arrive to our focus point, which is where the detectors are. And the detectors in this case are these CCDs, so these charge-coupled devices, which Andrea was also mentioning that they are at the end of these mirrors. So here are the 7 telescope modules of eROSITA, which have these nested mirror structures. And at the end of this, there is the CCD, which is recording the arrival times, the position on the CCD, and the energy of the incoming photons. So let's look a bit at the format of the X-ray data. What do you actually work with when you're working with X-ray data? We record the position, energy, and arrival time of these X-ray photons in this tabular format in the so-called event file. And from this event file, we can make images. So we can look at the X-ray photons as a function of their spatial XY information. Spectra, we can look at them as a function of their energy. Light curves, we can look at them as a function of time. And catalog, so we can use source detection algorithms to find these significant fluctuations above the background level and then compile their X-ray properties. And then furthermore, look at their multi-wavelength properties and so on. Of course, for all of these, you'll need information about the response and the effective area, which I'll explain on the next slide. Already Andrea was showing a bit about this before. But I wanted to link here some documentation about using X-ray analysis with eROSITA using the ESAS software. So here you'll find all the information on how to do more black belt X-ray analysis. But as Andrea was mentioning, you can also access already for example, the DR1, so the first data release products. The brightest sources are already extracted for you, these images, spectral light curves, on the DR1 website. So if you're interested in looking at those already to process, just go on the website or ask one of the team. So what are these response matrices and this RMF and ARF? So it's interesting to understand that, if you have an X-ray photon coming towards your X-ray telescope, there's not 100% probability that it will actually be detected. And there's not 100% probability that it will be detected with the energy that it actually has. So this is what's encoded in the response, so the RMF and the ARF. First of all, if we look at the ARF, which is here shown on the right-hand side, this is showing kind of how much of the detector and the mirrors that the incoming photon sees. So it depends on the filter, the optics, the mirror formats, and the CCD properties, the quantum efficiency, and so on. And then once it arrives to the detector, it can be detected with an energy that it has, but also in an energy that it's lower than it has. And this is what it's showing on this figure on the left-hand side, with the output channel energy and the input model energy here. So these are some things that we are encoding already in the model. So we have these response matrices, which we build into our models to account for these effects that we know that are happening, so that we get the correct physical intuition about our sources later on. Okay, so how does this actually work in theory? How do we look at spectra? So given that we work with event files, we count the photons, we don't measure the X-ray flux directly. So we need to convert our photons to flux using spectral models. And what we do is actually, this is the equation that describes this process. But if I explain this in words, what this is showing is that we're convolving our physical models, which describe this emitted photon density. This is like the actual spectrum of the source. So usually this is a power law, for example. In the simplest case, it's a power law, I would say. With the instrument response, so how is this incident emitted photon density convolved with what it's actually seeing in the detector and the mirrors to get our observed counts is what we actually detect. And so we have to forward model this because it's impossible to invert this in equation. There's too many errors involved. And that's why we do this modeling process to see which model describes our data the best and minimize the statistics to get the best fitting parameters to get this physical intuition about our sources. And this will also be clear in later tutorials. So don't worry if this is confusing, but it will be clear later in David's tutorial. Okay, so what does it mean in practice? How do I actually go about from my event files to get the different products? So, okay, first step is to retrieve the event files and clean them for various processes using these existing analysis pipelines, which I mentioned before in this documentation I linked on the slides before, that there's many existing pipelines to analyze and clean these event files. Then you can create an X-ray image to just have a look at what's going on in your image. And then you can extract the source and background information from the relevant regions of the image. And then from these source and background regions, you can extract the spectra, which you then will model using Bayesian X-ray analysis and a combination of PyXspec to learn about the properties of the source. And so Pietro will go through steps 1 to 4 of this to do, and step 5 will be shown by David later on. So this will all be much more clear in the next presentations. But I wanted to give an overview of these steps, just so you know what to expect in the tutorials. So what we're going to be doing is we're going to be modeling the ERAS-1, so the first all-sky scan data of a bright AGN, which is in fact this J1144. This is the most luminous observed quasar in the last 9 gigayears. And this is the spectrum that you would get at the end. This is what we're working towards. And we want to try and model this with an absorbed power law. So here is this absorbed power law. And maybe if you think about what I said on the previous slides, you can understand why this is not in the shape of a power law, or you can ask me at the end if you're interested. But yes, so let's see what we have to do first. Okay, this is the Bayesian X-ray analysis software that we're going to be using to analyze this spectrum. This is really great. It's very easy to install. You just pip install it. It's very straightforward to use and highly versatile. And it's really good if you look at the bottom here. BXA shines especially when systematically analyzing large data sets, when comparing multiple models, and when analyzing low-count data sets with realistic models, and realistically predicting the error bars in our models. So this is what we're going to be using. And so I mentioned the first step is to select the source regions and the background annulus to get our X-ray photons for the source. So this is this AGN here, this bright point source here, and then the background region from this annulus here. You can also see in other green circles, these other contaminating sources that need to be masked out from the background region as they are contaminating the true background levels. So this is where we're going to extract the source spectrum from and the background spectrum from. Now, one important point to make is that we're going to be simultaneously modeling the source and the background. So this is important because as you saw in the source region, there's actually also parts of the background, right? It's source plus background in that region. So what that is actually showing us is that it's a total spectrum. It's the pure source plus pure background. And so we can use the information from the annulus region, which is just the pure background, to inform us about the background level in the source region and model that simultaneously to get an accurate value of what the source spectrum is showing us. And this is maybe the most confusing part, but this will also, I think, be clear in David's tutorial later on. So as I said, it's very important to model the background instead of subtracting it. In this case, maybe it's not so important because this is a really, really bright quasar. So the background is orders of magnitude below the source for these lower energies. But as you can already see, as we get to higher energies, the total model here in the blue is beginning to be dominated by background. And if you have a source with much less flux, this actually starts coming in quite early, and you have to really better account for your background modeling in this case. So what we do is we use our pre-learned empirical background models to create a very well-trained background model for our observation. And importantly, we use C-statistics instead of chi-squared when modeling the background simultaneously. And this is also commonly used for low-count Poisson regime data. So chi-squared is used for Gaussian distributed data. And how do we actually go about doing this background modeling? So I guess, again, I said we use the knowledge of existing background spectra to inform the shape and normalization of the background spectrum that you have. So in this figure, I'm showing what's learned from around 3,000 eROS-1 background spectra combined to get the general shapes and structures of this background spectrum. And then basically we're trying to map this onto our current observation and add a few more Gaussians to best model our observation. And this is a good way to do it because it gives a much more accurate representation of the background because usually we don't have so many counts. And this is actually very easily implemented into this fit background.py Python code, which will be also clear in the tutorial later on. But if you're interested in more information, have a look at also these links. Okay, then the next step is finding the model for your source. So this is the physical model. Like this will tell us what properties of the source, for example, the photon index or the absorption levels in the source. And this will typically consist of a galactic absorption and host galaxy redshifted absorption. So absorption from our Milky Way and absorption from the galaxy that this source is living in. And then usually a power law component, which is typical shape of X-ray spectra. And maybe some complex components like Gaussian lines or black body emission. For example, a typical Gaussian line that we have in X-ray spectra is the 6.4 iron line, iron emission, iron K alpha emission. Okay, then the next step is setting up the priors to this Bayesian framework that BXA works with. So we're, of course, we want to make sure that we know where we're informing our model to do its fit in the best way possible. So we have to ask ourselves, where do we want our samplers, which are the ones kind of going around this parameter space of our model and converging to the best fit, where do we want them to spend most of their time? Do we want them to sample equally in linear or log space? And this is what I'm showing in this diagram here, where you see clearly what I'm trying to show you, that if you're sampling in log space, you're sampling equally, you're giving an equal weight to each order of magnitude. And this is usually done for parameters that vary over many orders of magnitude. For example, the normalization of the power law, which can go up or down by many factors of magnitude, given, for example, the brightness of the source. Alternatively, if we use uniform priors, so this was the log uniform priors. Alternatively, if we want if we only have a parameter that goes from around a few factors, so for example, the photon index, so how the power law changes in slope, we can use uniform priors in this case. And if we know very well, for example, the iron line, we know that it's around 6.4 kV, we can use Gaussian priors to really guide the measurements to that value that we know should be the correct answer. So, and we really need to make sure to set our priors in the reasonable ranges so that our fit will converge. Otherwise, if we set our prior to maybe 1 to 5 and our actual fit is at 100, of course, you will not get a good fit because the priors will not be able to go to the best value. So this is kind of really important part of the modeling process. And then skipping a few steps, but then all you have to do is run the solver and this ultraness sampler and plot the spectra using PyXspec. So this will be clear also in David's tutorial, but I would recommend you export the data from the BXA outputs and replot it yourself using PyXspec. Although BXA does produce default plots and chains and corner plots to show the best fit parameters, so you can also analyze them from there. Okay, so let's summarize. And I put here some questions that after my talk, hopefully you should be having an idea of how to answer. For example, what type of objects emit in the X-rays in our universe, and what can we learn about their properties using X-ray studies? What are the general properties of X-ray telescopes when observing the sky, and how do they collect X-ray photons? And maybe how is this different to radio and optical wavelengths? And then what are the steps I have to take before I can extract spectra and light curves from my source? And lastly, how do I analyze the spectra of an X-ray source using Bayesian X-ray analysis? Maybe the last one I'll give you some time still to answer that after the tutorials, but I hope this was helpful and I'm ready to take some questions.